Okay, we're going to continue on our discussion of laws or logarithms. This is part 2 of section 8.3, and there's nothing much that's new here. All I want to do is try a few more trickier questions and also show you a few word problems that use logarithms. Okay, so let's start with example number 1. These questions are kind of, I guess, a little bit different, where you're asked to kind of rewrite a logarithm using, I guess, letters or symbols, A and B in this case. What you have to understand here is you're going to use your log laws to try to rewrite the log expression in terms of A and B. So what we have here is the base 6th log of 2 is equal to A. And then we also have here the base 6 log of 5 equals to B. And they're asking you to solve or rewrite log base 6 of the 4th root of 20 in terms of A and B. So your answer, okay, will involve the letters A and B. So how can we do this? Well, you're going to have to try to find a way to rewrite this logarithm using your log laws. Anybody have an idea of what you can do first? That 4th root there, yeah, doesn't look too nice. So how can we rewrite the 4th root as an exponent? And if you said, oh yeah, you remember that as to the power of 1/4, I'm very happy. Well, once you've written that as an exponent, what log law can we use to, let's say, move down that 1/4? Yeah, so we'll use the power law now. And by using the power law, you can bring down that exponent to the front. So we'll have 1/4 log base 6 of 20. Well, that's good, but 20 and 2 and 5 are two different things. So I'm asking you to try to rewrite this as 2 and 5. So thinking, how does the number 20 get created by using the numbers 2 and 5? You may be thinking, hey, maybe it's time to actually prime factorize this number. Because if I were to prime factorize this number, remember that factor tree stuff? 20 is the same thing as 4 times 5. Of course, 4 is not prime, but 2 is. So lo and behold, you've just told me that 20 is the same thing as 2 times 2 times 5. Well, doing that now, I can rewrite this as log base 6 of 2 times 2 times 5, because that's the same thing as 20. How is this going to help me out? Well, at least now I see the 2 and the 5. I see also multiplication. So multiplication, in terms of the log laws, I can use the product law and rewrite these as addition. So 1/4. And now I'm going to ask you to rewrite this as addition. So log base 6 2 plus another log base 6 2 plus a log base 6 5. That's, of course, using the product law. And this is great because now I can finally make my substitutions. Because log base 6 2 is just equal to A. Here's another A. And then log base 6 5 is equal to a B. So, I think after simplifying, I'll have 1/4 2A plus B. Or if you want to write it as 2A plus B over 4, that works as well. There you go. Now, example number 2 is very similar, except in this time there's no A and B, it's this letter X. Okay, so I want you to kind of try the same kind of idea to see if you can simplify and write each of these expressions in terms of X. So example number 2, if log base 2 of 8 equals to x, express each logarithm in terms of x. So what can we do? Well, once again, how about trying to figure out 512 and write this in terms with an 8? Some of you might always know right away that, hey, that's just 8 times 8 times 8. That's great, because that just means that log base 2 512 is the same thing as log base 2 8 cubed. And then knowing that, now what laws I can use? Well, I can use that power law. And that allows me to bring the exponent down to the front. And then now I have 3 log base 2 8. Log base 2 8 is just x, so now I'll just substitute. And you get your final answer of 3x. Done. How about the other one? Log base 2 2. Well, you know this equals to 1, I know, but I want this in terms of x. So, you're going to have to figure out, once again, the 2 and the 8. How do they go together? 2 is equal to 8 to what power? I guess is my question to you. Well, you should know that 8 is 2 cubed. So going the other way around, I guess I take the cube root of 8, which equals to 2. And the cube root is just the power of 1/3. So this just becomes log base 2. And then instead of 2, I'm going to write this as 8 to the power of 1/3. And I think you can do the rest. So go ahead and do the rest. Done. Okay. Now, I know in section 8.2, we did those questions where we had to find the x and y intercepts. Let me see if I can find those for you right now. Remember those questions? 8.2. Let's go back to our 8.2 notes. Not this one. Let's see. Oh yeah, remember these ones? Yeah, right here, right here. Well, we found the x and y intercepts, and I said this is the actual, but I told you that, hey, I can't actually calculate that for you yet. Then you'll learn in section 8.3 how to calculate those things. Well, that's what we'll do next. So how do we actually calculate logs where the base is not 10? Because our calculator only has logs with base 10. Well, logs that are not in base 10 can be calculated using something called the change of base formula. And you're going to need to know this one in addition to the product, quotient, and power logs. Okay? Here's the formula, or here's the expression. Whenever you have log base c of x, that can be rewritten as log base d of x divided by log base d of c. Okay, where c and d, of course, are just positive numbers other than 1. So you can change this with any different base. So what we're going to do here is, because our calculator has base 10, that means what I'd like us to do is let the little d value there be equal to 10. And then we can actually calculate this number out. So for example, log base 5 100. By the change of base formula, I can write this as log base, and I'll use once again 10 of 100 divided by log base 10 of 5. Now, once again, the 10 and the 10 I've arbitrarily chosen. It could be 8, it could be 9, it could be 10, it could be 12, it could be 1,000, whatever. Why did I choose 10? Well, because that's the one my calculator allows me to use. So, all you need to do now is just go to your calculator and punch this in. Well, let's see what we get. So, I actually know what log base 10 of 100 is. That's easy, because that's just 2. So, I'll write this down as 2. Log base 10 of 5 is an ugly decimal, 0.6989, blah, blah, blah. So really, I would rather have you just type this all in at once to the calculator. So I'll say log 100 divided by log 5 and 2.86. There's your answer. Okay. So now you know how to evaluate logs of any particular base. What you need to do is just use the change of base formula and write them in base 10. Okay. It's time to move on to the word problems now. I'm going to go show you two that are very, very common in, I guess, life. First one's going to be talking about sound. I don't know if you know about sound intensity or decibels, but the sound intensity, and I'm going to use the letter B to represent that, in decibels is defined as this formula. It's B equals to 10 times log of the ratio of I to I naught, or I 0, where I, of course, is the intensity of the sound that's measured, and there's units for that, watts per square meter. And I 0, which is your initial intensity, is actually 10 to the power of negative 12 watts per meter squared. And that's what they call as the threshold of hearing. So that's like your baseline. Just like how we did the earthquake ones, we had this baseline. So here it says the sound intensity of a blender is 0.0001 watts per square meter. Find its decibel level. So all you need to do here is just plug this in. Finding the decibel level means finding out what B is. So B is equal to 10 times the log of the ratio of I, which is 0.001, divided by, and I naught is just 10 to the power of negative 12. Well, we can just go ahead quickly punch this into your calculator and find out what it is. So watch. 10 times log 0.00, oops, I missed a 0. 0.0001. 0.0001. Divide that by 10 to the power of negative 12. We'll close the bracket. Press enter. There we go. 80. Okay. So, there's our answer. 80 decibels. So, the units for decibels are dB. Excuse me. Well, how about this next one? It says the police car siren has a decibel level of 115. City traffic has a decibel level of 80. So the question is, how many times as loud as city traffic is the police siren? So how many times louder is it? Is it 10 times louder? I don't know what this is. What? 35 times louder? Like, how much louder is it in terms of this decibel scale? Well, to do this, let's actually find out the intensity of each of them. And then when we ask the question like how many times as loud, that's a ratio. We're going to use a ratio to try to calculate how much louder is one over the other. So first of all, I'm going to ask you to find the intensities first. Okay, so find intensities first. And we'll do it for each of them. So we'll do it for the police car. So the police car, where the B value is 115. So this equals to 10 times log of I divided by I naught. Okay, divide both sides by 10 to try to solve for intensity, which is I. So this is now 11.5 equals to log I over I naught. And then we're going to rewrite this in exponential form. So that becomes, remember, log is log base 10, so that's 10 to the power of 11.5 equals to I divided by I naught. I'm going to move the I naught or I0 to the side, so 10 to the power 11.5 I naught equals to the intensity. Just going to quickly box this right now because we'll use that again, but this is the intensity of the police car. Okay. I'd like you to do the same thing now for city traffic. AT equals to 10. You can do this on your own, by the way. It's the same thing, so practice. Okay. Notice I don't actually have an answer, but I have things in terms of I naught. And it's perfectly fine, because now I'm going to ask you how many times is loud, so I'm going to do a comparison or a ratio, and take the ratio of the police car decibel, or police car intensity, sorry, and divide that by the city traffic intensity. And doing that will allow me to figure out how many times is loud. 10 to the power 11.5 I naught divided by 10 to the power of 8 I naught. I naught cancels. I have 10 to the power of 11.5 divided by 10 to the power 8, which means we just subtract the exponents. 10 to the power of what, 3.5? And if you want a number, 10 to the power of 3.5, how about 3,162 times as loud? Wow. Yikes, that's a lot. Okay. Another instance where you'll see logarithms is if you're doing chemistry and pH stuff. I think we showed you an example of that before, but here's another one. In chemistry here, we've got this pH scale, and it's used to measure acidity, which are numbers between 0 and 7, or alkalinity, meaning the base, which is 7 to 14, of a solution. The pH of a solution is defined by this lovely formula. pH equals to the negative value, so negative log of the concentration of the hydrogen plus atoms. So just note that this is a logarithmic scale with base 10, because a pH of 9 is actually 10 times more alkaline as a pH than 8. So even though this goes up by 1, that going up by 1 is equivalent to 10 times because it's a log scale. Right? So in a study that compared pHs of different things, like urine to tears, here's the data from above table. And my question to you is, in part A, what is the concentration of the hydrogen ion in Bob's tears? Bob's tears have a pH of 7.4. So using the formula up here, I'm going to ask you to just find out the concentration of ions. So 7.4 equals to negative log H plus. How am I going to solve this? We're going to divide both things by negative, so I'm going to have negative 7.4 equals to log H plus. Then, once again, change to exponential form. And to do that, you get 10 to the power of negative 7.4. And that must be your concentration of H plus ions. That's it. If you want to calculate what that is, you can. 10 to the power of negative 7.4 Hmm. That's equal to, I think, on the calculator, 3.98 times 10 to the power of negative 8. And that'd be moles per liter. All right. Part B asks you, on average, how many times more alkaline are tears than urine? So when I compare, we notice that the tears are much more alkaline, 7.5 compared to urine, which is 6. But how many times more alkaline are the tears? Well, once again, to do this, you want to actually compare the concentrations. You want to find the ratio of the concentrations of both tears and urine. So I'm going to ask you, just like before in the sound one, to actually calculate the actual concentration. So let's do the urine concentration, please. We'll take the average number this time. So that'd be 6 equals to negative log h squared, or h, not squared, h plus. Move the negative to the side. Change the exponential form, so 10 to the power of negative 6 equals the concentration of the urine. We're going to do the exact same thing now with the tears, and I'm going to ask you to do that now on your own. I won't speak, but you should be able to do. And then to compare how many times more alkaline are the tears than the urine, just need to find a ratio. I'm going to do, in this case, the ratio of 10 to the negative 6 divided by 10 to the negative 7.5. That, of course, is just negative 6 minus negative 7.5, and that becomes actually 10 to the power of 1.5. And so the actual number of times is actually 10 to the power of 1.5. And if you use your calculator, 10 to the power of 1.5, that would be about 31.6 times. 31.6 times as alkaline. Okay. Now, this is kind of a long way of doing it. You could have also used this statement up here. See how it says a pH of 9 is 10 times more alkaline than pH of 8? To help us out. Because if I were to compare urine, which was 6, so that's here, right? Urine's here. And then tears is actually 7.5, so that's like right here. How much is the difference in the pH scale? It's 6 to 7 is 1, 7 to that is a half. So the difference in the pH scale here is actually 1.5. Do you see where I got the 1.5 from in my answer part B? 1.5. Oh yeah, 1.5. Because this is a logarithmic scale, we don't say it's 1.5 times more alkaline. Because this is a logarithmic scale, we have to go 10 to the power of 1.5. And that's why we get this 10 to the power of 1.5. So that shows it's actually 31.6 times as alkaline. Okay, last one. A pear is 15 times as acidic as Bill's urine. What's the pear's pH level? Well, let's figure out once again the hydrogen concentration of Bill's urine. 5.5. We'll do the urine concentration again. So urine concentration using the formula for pH, which equals to negative log H plus negative 5. Oh, sorry, not negative. 5.5 equals negative log H squared divided by negative gives you log H squared. Change the exponential form, 10 to the power negative 5.5 equals to the concentration of H squared. And because the pair is 15,000 times more acidic, I'm going to take 15,000 and multiply that by 10 to the negative 5.5 to show its hydrogen concentration level, which would be really, really acidic. So what would that actually be? 15,000 times 10 to the power of negative 5.5. That's not too bad, I guess. So 0.0474. 0.0474. Blah, blah, blah. So this is actually the concentration, the hydrogen concentration of the pair. To figure out its pH level, then, let's stick it into the pH formula. Negative log H plus, so negative log 0.0474, blah, 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 blah. And using your calculator, let's see what we get. So negative log. Answer. Whoa. A really small pH value. 1.32. Pairs pH value.